So here we are at our first of several units on calculus. And the project in this unit and the ones that are following is to come up with an analog or a generalization of the idea of a slope that will extend to functions that aren't linear. Okay, so what we want to do is generalize the idea of a slope to work for nonlinear functions. Just reminding ourselves of all the cool things that slopes tell us for lines. They tell us whether the effect of x on y is positive or negative, and whether it's big or small. Okay, so that's often what we want to know about functions that we're estimating with data, or functions that we're using to express our ideas in theory. Really, really helpful if we could have something that was the equivalent of a slope, but wasn't just limited to these very simple functions. And we are going to find it. It's going to be called a derivative, and that's what this unit is about. So what I want to start with, though, is I want to start with some aspects of slopes and lines that are helpful because they're so simple, but that don't generalize. Okay, so first I'm going to sort of set up the problem. Why is this a big deal to generalize the idea of a slope? Why isn't it just work seamlessly? So I want to start with I want to start by belaboring two things about slopes. Okay, so if we calculate the slope of a line of a linear function, how do we do that? It's delta y over delta x, rise over run. Okay, the first y value minus the second one divided by the first x value minus the second one, or you could do it the second one minus the first. Either way, it's just as long as you're keeping your x's and y's lined up there. It's the same for all x. So whatever starting value we pick for x, maybe I was calling that x0. I think I'm going to keep that notation. So wherever we start on a line, we're going to get the same value for the slope. And it's also the same for any delta x. We can take a big change in x or a small change in x. And just because this is a point that's an important contrast, let's check that I'm right about that. So let's look at the real simple linear function here, y equals 2x. Okay, so I can calculate delta y over delta x by picking a starting point, x0. Let's pick 4. So if I pick 4 for my starting point, then my y0, 2 times 4 is 8. Let's pick an easy delta x of 1. Okay. And once I pick delta x of 1, that's telling me that my endpoint, my x sub 1 value is 5. Okay, so 4 plus the change in x of 1. And then my ending value for y is the functional value of x. So 2 times x is 10. And I calculate delta y over delta x. And I get y1 minus y0, that's 10, minus 8, divided by x1, that's 5, minus x0 is 4. I get 2. Great. Okay, so what if I change x0? Okay, what if instead, let's start with 5. Okay, let's make 5, x is 5, y is 10. Our starting values, let's take the same delta x of 1. So now my ending value for x is going to be 6, going up 1. And my ending value for y is going to be 12. Fine. And so still delta x of 1 there. Calculate delta y over delta x here. Now in the top, my delta y, the y1 minus y0, that's 12 minus 10. And the delta x is 6 minus 5. I still get 2. Great. What if I change delta x? Let's go back to having 4 be our starting value for x. So 8 is our starting value for y, but now let's take a bigger delta x. Let's change x a little bit more, make it 2, so that now our ending value is 6. Ending value for x is 6, and f of 6 in this case will be 12. 2 times 6. Calculate, rise, overrun. I'm going to get 12 minus 8 divided by 6 minus 4. That sounds like 4 over 2 still equals 2. Okay, so punchline here is slope does not depend on what x value we start with or on how big a change we look at. It just is what it is. It's the same number for the whole line. And as I mentioned in the previous unit, sometimes we like that. Sometimes that simplicity is helpful just because it's simple. Sometimes it reflects, how much we can really infer from the data we have. So sometimes we like linear functions, but sometimes we don't like it. Sometimes we think that simplicity is too simple for the real world phenomena that we're trying to study, okay? Sometimes we're thinking about relationships between x's and y's where the impact of x on y isn't always the same, okay? If you're collecting volunteers for a campaign and the impact of your first volunteer might be really high, the second one might be also really high, but when you get to, I don't know, your 9th or 10th volunteer, the additional outreach, the additional voters contacted, the additional money raised, whatever they're doing, might not be as high. You can imagine in some contexts, even getting to the point where adding more people might have a negative impact because some of the people you're adding don't know what they're doing and they make a mess of things. Okay, so this is exactly the kind of idea we want to express with nonlinear functions, and it's the kind of relationship we want to pick up in the data that we study, okay? So we want to think about nonlinear functions. Go back to this idea. With nonlinear functions, what happens if we try to look at the impact of x on y, okay, the independent variable and the dependent variable, if we try to look at that just by calculating rise over run. So let's do that. Let's do that for simple nonlinear function. Everybody's favorite simplest nonlinear function is y equals x squared. Okay, so I'm going to do that same process, and I'll give away the punchline right now. What you're going to see is that with this function, the value we get for rise over run is going to depend on the x0 that we start with, and it is going to depend on the size of delta x. Okay, so let's check that out. So again, I think I'll start with x0 of 4. So now with this function, y is x squared. So if x0 is 4, then y0 is 16. And just as we did before, let's start with a delta x of 1 here. So we get x1 is 5, and y1 is 25. And we do rise over run for that, delta y over delta x. We get 25 minus 16 over 5 minus 4. 25 minus 16 is 9. Okay, so that's our slope. Okay, fine. So far, seems reasonable enough. Let's start now with just going to go through kind of basically the same process as I did before. Let's have the x0 of the x0 be 5. Okay, so my ending point from the first example is going to be my starting point here. y0 is 25. Again, I'll do a change in x of just 1 unit here, so that now my ending value x1 is 6, and my ending value for y is 36. And calculating delta y over delta x here, it's 36 minus 25 over 1. That's 11. Okay, I get a different answer. Said I would. Fine, let's just keep going. Now let's keep the starting point the same. Stick with one I had before here. X0 equals 1, Y0 equals 16. But now let's look at a larger delta x. So that x1 is 6, and now y1 is 36. And I calculate delta y over delta x. I get 36 minus 16 over delta, so that's my delta y, and delta x is 6 minus 4. So 20 over 2, I get 10. Okay, so 3 different numbers for what the slope of y equals x squared is. The calculating rise over run, the answer for that, rise over run, is different for different starting values and different levels of delta x. Okay. So one thing we want to ask, I think I'm going to focus on the second thing, the fact that actually, let me back up and say why I'm not going to focus on the first thing. The fact that rise over run is different depending on what x value we pick, that's actually a good thing. That's kind of often the reason why we are using nonlinear functions in the first place. Okay, so that idea that the impact of x on y might change whether we start at x equals 4 or x equals 5 or x equals 300, that the numbers might be different. That's actually kind of what we're looking for. Okay, so this is okay. I'll say more about it. It's actually better than okay. It's a good thing. The fact that it depends on x0, though, that's a little sorry, on delta x. The fact that the rise over run depends on delta x is a little bit problematic. Okay, so what I want to do to illustrate that is I kind of want to zoom in here on what we are doing when we are calculating rise over run for a nonlinear function. Okay, so I've switched here to a pre-made picture because I don't trust myself as an artist to write something that will make the point that I need to make here. I've also changed our nonlinear function to be y equals x to the 3 power, y equals x cubed. And really the reason why I'm doing this is that the impact of delta x, I feel like, shows up a little bit better with this function than with y equals x squared. Okay. So in this picture I've drawn, this is the function. This is y equals x cubed. That's the function that we care about. And again, here I'm picking a starting point. So that's messy. Let's make a thinner line here. So my x0, y0 point is 1, 1. That's a nice easy number to start with. And I'm thinking about a pretty small delta x here of 1/2. Okay, so I'm calculating rise over run here by starting at x equals 1, y equals 1, and taking delta x 1/2. And just as I was doing in the other examples, my x1 is x1 is 1/2. So then I use the function, I use this function y equals x cubed to calculate my y1. That's important. That's how we're making this about the function x cubed and not about some other function. So y1 equals f of x1. What is 1/2 cubed? It is 1/8. So that's how I get to this point here. Then when I calculate rise over run, what I'm doing here is, so I've got my delta y over delta x is 1/8 minus 1 divided by 1/2 minus 1. So just like before, I've got y1 minus x1 over x, sorry, y1 minus y0, it's delta y, divided by x1 over x0. And of course, I could switch it. I just change signs in both the numerator and the denominator, and everything would work out to be the same. Just like I did before, figuring out what that is, we get a -7/8 over -1/2. That turns out to be +7/4. Okay, so doing rise over run for this function gives me a slope of 7/4. That is the slope of a line. It is the slope of this line that we call the secant line. It's the line that's in blue here. This value, 7/4, is the slope of this blue line. Okay? And let's erase a little bit here because I don't want my picture too crowded up. I want you to be able to see that this line crosses the function that we care about at 2 points. That's what makes it a secant line. Okay, and you'll see what the contrast to that is in a minute. It crosses it at 2 points, and it's kind of close to the function. If you wanted to sort of say what is approximately the slope of this function y equals x cubed in this area, yeah, it's sort of 7/4, but it's not exactly that because there's space here, okay? The line, the secant line is not exactly equal to the function. Okay, so when we do rise over run for a nonlinear function, we're not really calculating the slope of the function itself. We're calculating the slope of a secant line that's cutting that function at 2 points, the 2 points that are defined by our starting x and y values and our ending x and y values. Fine. So let's just kind of gaze at this picture for a second. And as you're gazing at it, you might be thinking, well, you know what? If she picked delta x that was a little bit smaller, you might get a line. Terrible. See, you guys see why I have to draw my pictures in advance with the computer. But you might, if you picked a smaller delta x, you might get a line that is closer to the function. The secant line might be a better approximation. Well, yes. Lo and behold, that's true. So what I did in this picture is I picked a smaller delta x. So now delta x is 1/4. We're going from a starting point of 1, 1 to a starting point of 3/4, and 3/4 cubed is 27/64. So calculating the slope here, calculating rise over run, it is 1 minus 27/64, 1 minus 3/4. I think I might have switched my, I think I'm making this the starting point, and that's the ending point, but you'll see it doesn't matter here. All it does is affect the signs of numerator and denominator. So calculating that, I get 64 minus 27, kind of tedious here, divided by 1/4, that is 37/4. No, not 37/4, 37/16. That is what it is, and you can check me on that. Okay, that's a slope, and that's bigger than the slope that we got with the larger delta x. Okay, so when we took our secant line over a bigger change in x, it went from here to there, we got a flatter line, smaller slope than we're getting with the closer approximation here. So maybe this, we might be thinking, is closer to the slope of the actual function in black, what we actually care about. The line, the blue line is closer. And taking that same idea further, what we might be thinking is, okay, well, what's the right delta x to pick? What's the best value for delta x? We might be thinking the answer is as small as possible. The smaller delta x becomes, the closer the secant line is to the real function, and the closer the slope of that line is to the actual slope of that function, the function that's actually telling you how much a very, very small change in y, change in x, affects y. That is the answer that calculus gives us to the question of how do we find a slope for a nonlinear function. The answer is we let the change in x become as small as possible. Smaller than you can imagine. No smaller than that. Smaller, 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 until what we get is, instead of a secant line that is touching the function at 2 points, now we have what's called a tangent line. Okay, what makes it a tangent line is it just touches the function at 1 point. Okay, we would call that the point of tangency. Okay. So those secant lines that are passing through 2 points on the function, and we're picking those points closer and closer together, the line's getting closer and closer to the function. What we do in calculus is we imagine that distance between the starting value and the ending value becoming as small as possible. Smaller, smaller, smaller. We can't actually let it be 0 and still calculate rise over run. Okay. We can't have a delta x that is equal to 0, but what we can do, and what calculus invites us to do and empowers us to do, is think about the limit as this delta x is getting smaller and smaller. So we know it can't actually get to 0, but we can imagine what's happening as it is getting closer and closer and closer and closer. The slopes of those secant lines are getting closer and closer to the slope of the line that is just tangent, the line that is just touching the function at one single point. This, what I've got circled in red here, this limit as delta x goes to 0 of rise over run, that is the derivative. That is the derivative of f of x. We can also say the derivative of y. All right, that's kind of, pause for a moment, because that is kind of the big idea in calculus. Like, if we want to come up with these slopes for nonlinear functions, we're thinking about what people will sometimes call the slope at a point, or the instantaneous slope. Going back to the other issue, the issue that what that slope is depends on what value of x we're at. That's what we want. We want to capture the idea that the slope of the tangent line here at 1, 1 is steeper than if we picked a tangent line down here. This line would have a flatter slope. Okay, and what that's saying is that when we're down here at x equals, I don't know what that is, 3/8 or so, the impact of x on y is not as high as it is for higher values of x. So this relationship between x and y is one that's picking up speed. The more x we get, the more impact it's having on y. That's a point that we're going to talk about quite a bit in the next couple units. The touching base with the other issue that we had here, the fact that the derivative, that the slope depends on what x0 we start at, what value of x we start at. That's a feature, not a bug. That's something that we like. So lost my train of thought there, but now I found it. The point that I want to emphasize here is that the derivative is itself a function of x. All right. And I think for this lesson, I just want to close with some points about notation. So let's have one more page here. And yeah, so let's start at the beginning here. When we write delta x over delta y, from now on, that is the limit of a difference quotient, okay? It's not a limit, it is just a difference quotient. It's a quotient because we've got one thing dividing another, and those things are differences. The delta y means the difference in y's. Delta x is the difference in x's. We use this to talk about the slope of a line, and delta x really is a number that is greater than 0 here. When we take the limit of that, the triangles, the capital deltas, become lowercase Roman d's. Okay, so dy dx, that is the derivative. Okay, this is the limit of a difference quotient. And it is itself a function. And what else did I want to say about derivatives? Limit of the difference quotient is about a function. Oh, I know. And you can take the derivative of either a linear or nonlinear. If you take the derivative of a linear function, I think we're going to do that in a couple lessons. You'll see you get the same answer as the slope. So this is one way to write the derivative, and it's something that you'll see a lot. Another way to write the same thing equivalently is f prime of x. Okay, so this is also the derivative. So sometimes people will say this is the derivative of y with respect to x, the derivative of f with respect to x. Remember that y is f of x, so those really are the same things. We're emphasizing the x. At this point, it seems kind of gratuitous, but towards the end of Math Camp, we'll be talking about functions that depend on more than one variable, and so it's going to be important to keep track of, are we taking the derivative with respect to x or some other variable here. These two types of notation are both widely used. Okay, so they really mean the same things. Okay, these are equivalent. And they have, I guess they're both in use because they have different advantages. The f prime notation here, that is really helpful when we want to put in specific values. Okay, so if we wanted to say what is the a derivative evaluated at the point of x equals 1. Okay, for the function that we were just looking at, that y cubed function, the derivative at that point is 3, and we might contrast that to the derivative evaluated at x equals 2, which is 12. You don't know why those are those numbers yet. You have to stay tuned. I'm asserting that that is true. We'll see by the end of, but really by the middle of the next unit, you'll know why this is true. All I'm saying at this point is this notation is super useful when we want to be plugging in specific x values and getting specific values for the derivative, okay, for the slope at that particular point. For the instantaneous slope, sometimes people will also call it like the marginal effect, and all these ideas are getting at the same thing. What is the impact of the smallest possible change in x on y? The other notation, the dy dx notation, that's useful in other contexts. One that I'll mention here is kind of a related version of that. So dy dx is, when we write it like that, that is the same thing as the derivative, and it is itself a function of x. It's kind of related to this command, ddx of f of x. What we would say here, this is telling us spell words wrong. This is telling us take the derivative of f of x. Find the derivative. Okay, so written like this, this is a command. You can also think of it as an operation. Okay, so taking derivatives are operations that we perform on functions. Okay, so that's kind of a lot of setup. Where we're going to go in the next 2 lessons is we're going to have a little interlude lesson on limits. Going to be a little bit quick there. You could do a whole class on limits. You could do more than one class on limits, but I'm going to try and give you enough of the ideas that you'll understand how we apply them to difference quotients. And then in the lesson after that, that's exactly what we're going to do. We're going to find derivatives of function by taking limits. So I'll see you then.